So, we shall continue with what we were discussing in the last class. So, rather we shall be trying to like look into the S-Box design. We shall be trying to see how we can develop the AES-Box design, and by applying the techniques of isomorphism that we were discussing in the last few classes. So, the concepts that I will be trying to cover in today's class is rather to take a deep look into the S-Box implementation. So, this is something that we shall be trying to cover in some of the next classes as well, and talk about getting a composite field AES, that means where the entire AES is implemented in composite fields. Okay, then these are important thing because like as you probably have understood by now, that when you are doing when you are doing the operations in composite field, then you also need to do a field transformation from the input field to the output field. That means from the field gf to the power of 8 to gf to the power of 4 square and vice versa. So, in order to diminish that, we often implement the entire AES in composite fields, okay, and that is what we shall also be trying to look into, and finally conclude with a quick comment about the Intel AES instruction. So, again let us come back to this slide where we were discussing about the S-Box on composite fields, and we will try to take a quick look into this architecture. Okay, so how essentially it works. So, in order to do that, I will try to tell you of or rather go into the math of this design. So, in particular, right, let us try to see that suppose you have implemented or you have developed a design where you essentially have broken up the you have got the design in gf to the power of 4 square. That means you have basically transformed the element from gf to the power of 8 to gf to the power of 4 square. So, what I want now is that I want to calculate the finite field inverse now in this field, right. I want to calculate the finite field inverse in gf to the power of 4 square. So, that is my what I said as the composite field. So, I want to know how to calculate my finite field inverse in this particular composite field. Okay. So, how does an element in composite field look like? So, like as I said that when you are implementing a field in gf to the power of 4 square, that means there are two parts of this polynomial. The first part is say say let us tell it is gamma 1, and the second part is say gamma 0. Okay. So, therefore, right, the way you can read this element is a polynomial which is say gamma 1 y plus gamma 0. So, note that each of these elements gamma 1 and gamma 0, that means gamma 1 comma gamma 0 are both elements in gf to the power of 4. Okay. So, they are elements in the finite in the composite in the field gf to the power of 4. So, now what I want is I want to calculate basically write this, that is I want to calculate gamma 1 y plus gamma 0 whole to the power of minus 1, because I want to calculate the finite field inverse, and I want to do this modulo my irreducible polynomial. So, what is the irreducible polynomial here? So, remember the irreducible polynomial here is Ry, which is denoted as something like y square plus tau y plus mu. Okay. So, remember that when we are talking about composite fields, then we were doing this modulo qy px kind of thing in the last class, and that essentially is like one of these polynomials is this, where you are basically handling elements in gf to the power of 4 square. So, for doing this, right, we have to also understand first that how you do multiplication in this field. Okay. So, let us take this element like gamma 1 plus gamma 0 and try to multiply it with say delta 1 y plus delta 0. Okay. So, when you are trying to do this multiplication, remember that so let us try to do this multiplication. Okay. So, therefore, if I just apply the school book operation, then the first then I do this, right, I get gamma y square, and the coefficient for this is gamma 1 delta 1. Likewise, if I take y, then the coefficients are gamma 1 delta 0 plus gamma 0 delta 1 plus gamma 0 delta 0. Okay. So, note that here I have exceeded the the limit of this field, that means the degree is now y square, and therefore, I do a modular reduction with this polynomial. Okay. So, in order to do that, again what I do is this, right, what we basically substitute y square with tau mu, sorry, this is like so this would be y. Okay. So, basically it is tau y plus mu. So, therefore, I substitute this by like tau y plus mu. So, that means y square will be substituted with gamma 1 delta 1 and y square will be substituted with tau y plus mu. Okay. And then you have of course, you have got y into gamma 1 delta 0 plus gamma 0 delta 1 plus gamma 0 delta 0. Okay. So, now if I just combine, right, then I take out and bring y or the coefficients of y at one place, then I have got gamma 1 delta 1 tau plus gamma 1 delta 0 plus gamma 0 delta 1 plus the constants, which is gamma 1 delta 1 mu plus gamma 0 delta 0. Okay. So, this is what we have when we are doing this multiplication operation. So, remember that so now what we want is that we want to basically calculate. So, we basically we want to compute a value which is say denoted as delta 1 y plus delta 0, such that like delta 1 y plus delta 0 multiplied with gamma 1 y plus gamma 0 mod of r y should give me 1. Okay. So, this implies that I basically want to calculate a delta 1 y plus delta 0, that means essentially this part, such that this result is equivalent to 1 mod of r y. Okay, mod of r y is essentially this y square plus tau y plus mu. Okay. So, that means, right, what I want is, since I want this to be equal to 1, that means this to be congruent to 1 modulo this field, what I basically end up in is in having two equations. So, the equation 1 is essentially gamma like gamma 1 delta 0 plus gamma 0 delta 1 plus gamma 1 delta 1 tau, which is essentially this part. Okay. So, this essentially is equal to 0, because I do not have any y term here on the right hand side, whereas the other part, which is gamma 0 delta 0 plus gamma 1 delta 1 mu, right, this is equal to 1. So, I have got two parts here. Okay. So, you can imagine that I want delta 0 and delta 1. So, basically I can just rewrite this, right, essentially, and write that this is nothing but delta 0 gamma 1 plus I can take delta 1 common, and I have got gamma 0 plus gamma 1 delta 1 delta 1 is taken common. So, I have got gamma 1 tau, okay, and this is equal to 0, and I have got the other part, which is delta 0 gamma 0 plus delta 1 gamma 1 mu, okay, and this is equal to 1. So, now I have got like two equations, and I have got two variables to solve, that is gamma 0 and delta 1. So, how do I essentially solve them? We just apply simple simple technique, where I basically I just multiply this equation. So, there are two equations here, 1 and 2. So, I just multiply 1 by because I want to eliminate say delta 0. So, I multiply this by I just multiply this by gamma 0, and I multiply this by gamma 1. Okay. So, therefore, if I do this, then what I get is this, right, I get so if I just multiply this, then I get delta 0 gamma 1 gamma 0, okay, plus delta 1 gamma 0 plus gamma 1 tau multiplied with gamma 1, and that is equal to 0. Okay. So, I have multiplied, sorry, this should be gamma 0. So, I have multiplied gamma 0 here, and the first term is delta 0 gamma 0 gamma 1, because I am multiplying gamma 1 here, plus delta 1 gamma 1 square mu, okay, and that is equal to gamma 1. So, therefore, now if I add up these terms, remember it is in GF 2 power of 8. So, basically I end up getting gamma 0, and then these two terms gets cancelled. So, I have got gamma 1 square mu plus gamma 0 plus gamma 1 tau, okay, and essentially I have got I basically have taken delta 1 common. So, this essentially multiplies with gamma 0, okay, and finally, I essentially get gamma 1 on the right side. So, therefore, I can do a simplification where I essentially I can bring this to the right hand side, and therefore, this is nothing but delta 1 is gamma 1 multiplied with gamma 1 square mu plus gamma 0 plus gamma 1 tau gamma 0, and this I do an inverse. So, basically I calculated an inverse, but note that this inverse is in GF 2 to the power of 4. Okay. So, therefore, this inverse is done in a smaller field, which is GF 2 to the power of 4. So, therefore, right, what we get here is that delta 1 is gamma 1, okay, and essentially, right, you can also just do a few simplifications here, and you basically can get here, this is nothing but like gamma 1 into gamma 0 square plus, if I multiply this, you get gamma 0 gamma 1 tau plus gamma 1 square mu, okay, and this is we do an inverse. Okay. So, therefore, right, this is essentially the equation that you get for gamma 1. So, likewise, right, you can take this gamma 1 and you can plug into this equation, and from there you should be able to get delta 0. Okay. So, like we have got delta 1 here, so you should be able to get delta 0, and it turns out that delta 0, if you just apply this and just plug in over there, you will get delta 0 is gamma 0 plus gamma 1 tau multiplied with again this inverse, that is gamma 0 squared plus gamma 0 gamma 1 tau plus gamma 1 square mu whole to the power of minus 1. Okay. So, this gives me the two parts which I want. So, I am able to calculate gamma delta 0 and delta 1. So, therefore, right now I essentially take this input, that means I take gamma 1 y plus gamma 0 as an input, and the inverse essentially is done now in GF 2 to the power of 4 square, and the final result is also in GF 2 to the power of 4 square, and the result is denoted as delta 0 y plus delta 1. Okay. And the equations or transformations are essentially given by these two equations, say equation 3 and equation 4. So, you have got equation 3 and equation 4 to tell you what are these transformations. So, once you have done this, right, then we can now go back to our slide, and we can see that essentially that is being okay. So, that is being exactly done here. Okay. So, you can see here that essentially is being done here, where we would like to like do this inverse calculation now in GF 2 to the power of 4 square, and if you observe here that these are your inputs, this is an input, right, this is an input A which is in GF 2 to the power of 8, we do a map and then get the result in GF 2 to the power of 4 square. So, this higher part is essentially, or AH as written over here, is essentially nothing but your gamma 1. Okay. So, this is your gamma 1 and this is your gamma 0. So, therefore, what I do here is I now like I can annotate here like based on the previous discussions, and let me see. Yeah. So, what I can do is I can try here and write this as say gamma 1. So, this is my gamma 1 part. Okay. So, this is my gamma 1 and this is your gamma 0. Okay. And now I calculate delta 0 and delta 1. So, this is my delta 0 and this is my delta 1. Okay. So, now note that what you basically if you remember, like what the equations that we had was as follows. So, we had delta 0. So, we had so this is your delta 0. So, we had delta 0 as equal to gamma 0 plus gamma 1 tau multiplied with gamma 0 square plus gamma 0 gamma 1 tau plus gamma 1 square mu whole to the power of minus 1. Okay. So, now you can note that that exactly is essentially this part here. Okay. For example, this is the GF 2 to the power of 4 inverse. So, this is this inverse which is being computed. So, therefore, right, the input to this inverse is essentially your So you have got gamma 1 as this input, so you do a squaring here, so this becomes gamma 1 square, okay, and then you do a multiplication. So note that this multiplication is with a constant, okay, so and this constant is nothing but mu. So you basically calculate gamma 1 square mu here, okay, and here you do a so here you basically calculate so this is your nothing but gamma 0 plus gamma 1, and that is passed here, and this input is gamma 0. So therefore when you multiply this, you get gamma squared plus gamma 0 gamma 1, okay, and that is your like this part. So here like what we have assumed is this tau we have assumed to be 1, okay, so you can do that, and if you do that, then this is your part gamma 0 square plus gamma 0 gamma 1, and that you add with gamma 1 square mu, and then you pass it to the input of this, and therefore you get you pass it to the GF to the power 4 inverse, and you get this result, okay. So now you multiply this with this part, which is essentially like your gamma 0 plus gamma 1, okay, and gamma 0 plus gamma 1 is therefore passed here, and you get the corresponding like output. So likewise, right, you can see that when you are doing this, the other part also can be observed here. So again, this is the other part of the inverse, you again do a multiplication. So therefore the other part, if you write, remember that it is delta 1, and delta 1 was annotated as gamma 1 multiplied by this inverse. So again this same thing is written here, that is gamma 0 square plus gamma 0 gamma 1, again tau is 1, so plus gamma 1 square mu whole inverse. So you multiply this by only with gamma 1, okay. So that is essentially this part where you are, so in one case you are multiplying with gamma 0 plus gamma 1, and that is this part where you are multiplying with gamma 0 plus gamma 1, and this is the other part where you are multiplying with only gamma 1, okay. So therefore this is here you are multiplying with only gamma 1. So anyway, so therefore, right, this turns out to be that this is your, rather I would say, delta 1, and this is your delta 0, okay, and that is essentially the two parts of the output that you get. So finally when you have got this output, which is in GF to the power of 4 square, so GF to the power of 4 square, the output that you get here is nothing but delta 1y plus delta 0. So these are the two parts here. So this is the higher part, so this is your delta 1 and this is your delta 0. So you get this delta 1 and delta 0, and then you apply the inverse affine transformation to get the result back in GF to the power of 8, okay. So how do you get this GF to the power of 4 inverse? So you can actually apply this trick in a recursive manner. Therefore if you apply this trick in a recursive manner, you again can get another alternative architecture, and therefore now you have basically decomposed GF to the power of 4 to GF to the power of 4 square, okay, and therefore, right, this operation now is when you are GF to square. So therefore when you are doing this, then you can note that the inversions will be done in a smaller field, okay, and therefore you can actually like do this GF to the power of 4 multiplications, GF to the power of 4 squarers, and all of them can be decomposed into further subfields, and you can do them in smaller fields, okay. So with this background, right, you can see that if you can see the benefits, because you can see that when you are doing this operation, you can observe that the gate counts that essentially happens, right, is significantly reduced, and therefore there is a lot of saving when you are adopting these kind of tricks. So now of course, like when apply the same trick for the inverse S-box, and here are some savings for some costs for the inverse S-box. So the inverse S-box, when you are doing the inverse S-box, when A is not equal to 0, then you have to again apply the same trick, but you have to first apply the inverse affine, and then you have to do the inversion computations. When A is equal to 0, of course you have to do the 0 on the inverse affine, and then you have to calculate the corresponding inverse. So when you are doing this inverse S-box in like composite fields, then again the gate count requirement in terms of NAND gates is around 182, and therefore you have got similar amount of resource requirement for the inverse S-box as well. So therefore, right, when you are trying to adopt this technique for representing or implementing a composite field S-box, so remember that you have to do a mapping and reverse mapping from GF to the power of 8 to the composite field and back. So an alternative, so because of if you want to redo, and you have to do it per S-box computation, okay, and therefore this conversion can add to a bottleneck. If you really want to develop an alternative approach where this bottleneck is alleviated, one alternative approach would be to convert all round transformations into the composite field. So you basically do a transformations at the only beginning, like when you have got the plain text and the key, you convert the plain text and the key to the composite field and then write the entire AES in composite fields. Okay, so you basically design the entire AES in composite fields, and finally you get the result in GF to the power of 4 square or your chosen composite field, and you then just do an inverse transformation to get the result. So in that case, the transformation overhead is only at two places, at the beginning and at the end, but you are not doing it per S-Box or per computation. Okay, and that can significantly reduce the bottleneck. So therefore, this would just require one mapping and one reverse mapping for the entire encryption or decryption, and the operations like add round key and shift rows are of course not altered, but the mixed columns have to be re-implemented like the S-Box. Okay. So let us try to take a look. So like about the overall architecture in that case. So when you are doing this, this is probably one architecture where you are doing both encryption and decryption on the same hardware. So as I said that if you want to improve the throughput, then there are several techniques that you can try to adopt. For example, you can try to multiplex the data, the input data, so that so that it's because you remember that there is a pin count restriction. So if you really want to save on to that, then you can multiplex the input to the encryption engine and to the decryption engine. You can also try to adopt pipelining, so that if you want to pipeline say the encryption unit in a round by round manner. But remember that when you are doing pipelining, yes, the throughput will increase, but you will not be able to support certain modes of encryption. For example, right, you can reflect on this point that when you do a pipelining, then there is no advantage when you are wanting to have say a cipher block chaining or what is called as CBC. Okay. On the other hand, there may be some modes of encryption where pipelining would give advantage. So that depends upon what or how you want to use your AES block cipher. You can choose to apply pipelining or not to apply, but yes, at the same time when you are applying pipelining, there is an increase in area, but there is also an advantage in terms of throughput. Likewise, we would also probably want an instantaneous toggle between the encryption unit and the decryption unit, and also as we discussed about the Galois subfield, if you do that, then there is an overall compact implementation. So therefore, right, I mean you can actually like depending upon this, you may probably want to like do this operation, so that when you are doing encryption, then essentially one part of the circuit gets active, but when you are doing decryption, then there is another part of the then the modes get reversed, because now the input will be a cipher text and the decryption unit should be able to decrypt on the fly and give you the result, which is your plain text. But one important thing, as I mentioned, is that the entire thing should have now has to be represented as in the composite field. Okay. So for example, let us try to look into the SubBytes first. So in the SubByte, this is your transformation in the plain and simple way. You are doing a finite field inverse, then you are doing an affine mapping with A and B. So these are your pre-chosen vectors, and I mean vector is B and matrix is A. So when you are trying to implement in composite fields, remember there is an initial transformation. So therefore you take your element Y, apply the T matrix which you are choosing, or which you essentially develop for converting your element to GF to the power of 4 square, say, or GF to the power of 2, your chosen composite field, and then you get the result in Y dash. So you do your computation in Y dash. Okay. So therefore, right, what you want is this Y is nothing but if you plug in this Y equal to AX inverse plus B into this equation, then you are basically doing this, right? You are basically doing AX inverse plus B, and then you are applying a T map on that. And remember that T is a linear mapping, so I can distribute this like this, so I can get TAX inverse plus TB. Okay. So basically what I am trying to explore here is that I am trying to explore whether I can combine the like the composite field inverse with the affine mapping in one single shot. Okay. So if I do that, then you will see that I have got TAX inverse plus TB. Okay. So what I can do is I can write this X inverse as Tx inverse, okay, and I can essentially bring in a T inverse factor and I can remove it by again multiplying with T. So T inverse T is I. Okay. So I can equivalently write this in this form, but if I do that, then essentially you can see that of course I have got TB also, but then what I can do is now I can think, right, that this TAT inverse is my new matrix A dash, is a new matrix A dash, and TB is a new vector denoted as B dash. Okay. So now this internal part is what? It is Tx inverse. Okay. So that means it is nothing but I am doing the inverse X inverse and then I am applying a T mapping onto it. Okay. So that as if like this X inverse is an element in GF to the power of 8, and then I have applied the T output or applied the T matrix on it and converted into GF to the power of 4 square. So that means now I can do my computation. So what I can do now is that suppose my computation of the finite field inverse is in GF to the power of 4 square. Okay. So rather than like bringing the result back and forth from GF to the power of 8 to GF to the power of 4 square or GF to the power of 4 square back to GF to the power of 8, what I can do is that I can simply compute the entire thing in GF to the power of 4 square. Okay. That means the S-box is in GF to the power of 4 square. And finally, when I am doing the affine mapping, rather than bringing the result back to GF to the power of 8, I do this computation in GF to the power of 4 square. But when I am doing the mapping in GF to the power of 4 square, then I cannot apply A and B as my affine vector matrix choices. But rather, I have to replace these vector matrix choices by these matrices TA, T inverse and TB. Okay, that means A dash and B dash. Okay, so now once you have done that, right, then you can do this computation here, and there are some interesting observations that you can make at this point to understand the advantages of these chosen parameters. For example, the irreducible polynomial which I chose was y squared plus y plus tau. So remember I made this one also when I was discussing about the S-box. So here tau is often a primitive element of GF to the power of 4, and we choose this tau as often say omega power of 14, where omega is say x, okay, which is essentially nothing but an element on GF to the power of 4. So what it means is, just simply put, these are some like some chosen parameters that I choose for this irreducible polynomial, say Ry. Okay. A key point here is that if you choose this, for example, then these choices will actually have a variance on these matrices A dash and B dash. Okay. So interestingly, here is a comparison. So this is your original matrix A, which I had for the affine computation, and when I transform them, that means when I transform them by using this equation T a T inverse, then my resultant matrix is as follows: A dash. If you compare the number of ones here, the number of ones is something like 40, and it has reduced to only 18 values. Okay. So that means now if I want to use gates for representing, for implementing this matrix versus like implementing this matrix, you can easily understand that the number of XORs will be significantly reduced. Okay. If I want to implement this 0-1 multiplication, I just need an XOR. Okay. So this you should be able to think about. I just leave it to think that if I want to implement this matrix with a vector multiplication, then the entire circuit will operate only with XORs. There is no other gate which is required. So therefore here the number of gates which will be required will be proportional to this number of ones in this matrix, which is 40. Compare it with this implementation where it will be proportional with only 18. Okay, and therefore there will be a significant amount of saving when you are choosing the proper choices. So now let me just conclude this part by discussing about the final effect of these optimizations on scaling and squaring. Okay. So therefore scaling and squaring is nothing but calculating mu into gamma squared. Remember that gamma is now denoted as gamma 1z plus gamma 0, and then I am doing a whole square on that. So if I do that, I will get gamma 1 square z square plus gamma 0 square. Remember that I am doing in characteristic 2, and then we will replace z square with z plus n. Okay. So therefore if you do that, you will get this as your result. And remember that mu, which is with which you are doing the scaling, is a constant, and that is essentially nothing but delta 1 z. Okay. Remember delta 1 cannot be 0, so it is some delta 1 z, and this delta 1 is say n to the power of minus 1, as we have taken as a choice. Okay. So n to the power of minus 1 is again equal to n square, because n to the power of 3 is 1. Okay. You can easily understand this because n is an element in GF 2 power of 2. Okay. If you do that, right, then there are 4 elements, and therefore right, you can verify from Fermat's little theorem that you will get n to the power of 3 as 1. Okay. So therefore right, you can actually write n to the power of minus 1 z as n squared z. Okay. And therefore right, it turns out that mu gamma squared is nothing but, I am writing n squared z, multiplying it with gamma squared, which is gamma 1 squared z plus gamma 0 square plus n gamma 1 square. So now if I apply n square over this part in the parenthesis, I will get n square gamma 1 square z square plus z multiplied with n square gamma 0 square, where I am multiplying this over this, and then I have got n to the power of 2 into n, which is n cube. Note that n cube is 1, so I get gamma 1 square. Okay. So this you can again write as n square gamma 1 square z square plus z into n square gamma 0 square plus gamma 1 square. This is just copying this result, So, this is equal to n squared gamma 1 squared, and now I can write z squared as z plus n. So, I replace z squared with z plus n because I am doing a modulo with z squared plus z plus n plus z into n gamma n squared gamma 0 squared plus gamma 1 squared. So, therefore, now if I just take the coefficients of z and the constant part, then I will have z into n gamma 1 squared plus n squared gamma 0 squared plus gamma 1 squared. Okay. So, note that you can easily verify that I have got n squared, is easy to verify that you have got n squared gamma 0 square which comes here, but the other term, that means if I take gamma 1 squared, I will get n squared plus 1, okay, and n squared plus 1 is nothing but n, because n squared plus n plus 1 is equal to 0. Okay. So, therefore, this is your corresponding operation when you have done scaling and squaring. This is your final result here. I mean, this is the result till this point. So, now if you observe, you can see that you have got scalings, there are some intermediate scalings which you are doing. Okay. In order to realize this scaling, hierarchically you are doing another few, you are doing 2 more scalings. For example, here you are doing a scaling with n because you are multiplying with n, okay, and likewise here you are doing a scaling with n square. Okay. And the other operation is, of course, you are doing an addition. So, you are also doing an addition here which you are doing. Okay. So, these operations are now essentially also needs to be tackled and needs to be again implemented. So, these operations can in turn be therefore converted to elements in GF 2 power of 2 whole power of 2 and again computed in the subfield GF 2 power of 2. Okay. So, these operations are in GF 2 power of 4 because you have now successfully decomposed a GF 2 power of 8 operation into GF 2 power of 4. So, therefore, these operations, that is the scaling, the addition, all of them takes place in GF 2 power of 4, but you can also equivalently write GF 2 power of 4 isomorphically in this field GF 2 power of 2 whole power of 2, okay, and therefore, you can compute in the subfield now GF 2 power of 2 modulo again S z which is equal to z squared plus z plus n. Okay. So, therefore, this is something that we need to essentially again take a look at, and we need to kind of continue about how we can or what is the impact of these optimizations on this overall circuit. Okay. And that is what we will take up in the next class. Okay. Thank you.